Hello, hello, hello. Can you hear me? Yes, good afternoon. All right, I'm going to take that to mean that you can hear me. All right, awesome. Good afternoon, David. Good afternoon, Jalali. Good afternoon, Liani. I love this part. Good afternoon, Hoyin. Oh, he's fast today. Good afternoon, Hoyin. Good to see you. Oh, sorry. Good afternoon, Noelia. Good afternoon, Shomari. Good afternoon, Renice. Good afternoon, Tomika. All right, I like that. Good afternoon, Michelle. Good afternoon, Juanita. Oh, and someone's coming in and blah, blah, blah. The waiting room, the waiting. Okay, who can see your recording? That's interesting. Who can see your messages recording? Oh, okay, wait, more people coming. Okay. Good afternoon, Jean-Pierre.
Good afternoon.
Thank you. Good afternoon, Catherine. Thank you. Good afternoon, Shankia. So I'm getting a weird, oh, there's a weird Zoom update. Quick question on the sidebar. I'm still under the impression that when we use these YouTube videos at all, for whatever, I'm still under the impression that when we go to the recordings and the YouTube videos, the chat does not come through, right? If anybody knows any differently, or if anybody knows how to access the chat on the YouTube video, please let me know, because I am getting a weird message right now that seems to indicate that maybe that's possible, which would help. But okay, anyway, good afternoon. Yeah, there's no chat on YouTube. That's what I thought. That's what I thought. And someone complained about that. And I don't know. I do think you all do get chat logs, like as text files if you care. But right, I mean, it doesn't really help much. But right, I'm getting a weird message right now that says you can see your messages recording on. I don't know what that really, I assume that's just a warning, but okay, anyway. Hello. Okay, we're going to start. But thank you, Catherine. That totally counts as a blah, blah, blah. As a thingy thing. That also reminds me really quick. So we're going to get to stuff. Hopefully, I always say this quick. Oh, it's part. Okay, it is a, thank you, Renice. That is totally helpful. Right. It does seem like it's part of the Zoom update. Okay, but it's just like a thing, right? It's not actually.
Good afternoon, Professor.
Oh, good afternoon. Oh, I like that. And by the way, thank you. That is Edie. And all of you, by the way, I'm finding a lot. Excuse me for 1 minute. Request from another dimension. Hold on a second. Where is that actually? Wait, where? Oh, right there. Okay. Wait. Good afternoon. Yes. Good afternoon, Edie. Thank you, Renice. Quick points on the game turn assignments, because I really do think you guys seem to understand them, frankly, better than anybody has in past semesters. Maybe we're all just getting used to. But since you all do seem to understand them, and you seem to understand that, like, some apply to some of you and some apply to others, which is great. Let me re-encourage you to remember, there is one that may have gotten lost in the shuffle because I put it so early. Anytime you use your voice at all to say anything, I mean, including hello, but if you use your voice, that is a special separate game portal that you get points for. Because I mean, just remember, you totally can get points when you use your voice, like two people just did right now. So that's one thing. Also, I just put a new one in case. So far, this only applies to one person. I mean, I just put in a new portal. Like, most of you will be confused by it, maybe. Oh, good afternoon, Kirsty. Awesome. But like, if for some reason there's a glitch ever, and like I owe you points, but I can't get them to you for some reason, that's happening with one person right now, and I can't figure it out. So it might happen with others. If for whatever reason I just, like, it won't accept your assignment, but you and I can see that, we both see that you've done the assignment, but like Google Classroom is just not, for some reason, doing something, then that's why this new portal that's called Glitch Portal or something is for that, like for you just to get your points there instead. Again, just use it if you and I have already had if I say, like, go use the Glitch Portal, then that's what it means, and otherwise you can ignore it. Good afternoon, Vince. Good. Yeah, right. So it was Catherine. So thank you for, yes, it was Catherine. Right. So Catherine and everybody else, since for some reason Catherine has an assignment that it just won't accept. I don't know what the deal is, and it's like stuck. But I can see your assignment. I've graded it, but it won't let me give her the points. So I made up this glitch portal so that she can just get the points there instead. And that, of course, is for anybody if this comes up with anybody or everybody else. But that's what it is. And until it comes up, you'll know it when it comes up with you personally. Good afternoon, Aja. Thank you. Okay, for saying that. Okay. What else? All right. Now, I want to get to material. Specifically, you may have noticed, oh, and don't forget, like, I do feel like some people, I feel like the YouTube videos are working for some people. So again, just remember, you can totally get points for any evidence that you've in any way referred to any of them. And I can't imagine a circumstance where anybody would sit down and watch an entire one of these classes just like for, but I can imagine scenarios where you'd have it on in the background or you'd scroll around and find the thing you need, blah, blah, blah. And again, I think most of classes, even though I try to explain stuff in class, I don't really think the point of class is for one person to explain and then the other person to, in that moment, understand. Like, it's lucky when that happens, but it's mostly about, class is mostly about you hearing me explain the thing that I'm trying to explain so that oh God, he really cares about that. That's something that's going to be on the test. It's like class is about finding out what it is that you have to figure out. If you're lucky enough to figure it out while I'm talking about it, terrific. But often it's take my explanations more as like highlights of, okay, this is the thing to think about at home. Okay, that said, I think we're all here. Hello, hello, everybody. Who have I not said hello to? Hello, Antonio, if I didn't say hello. I think I said hello to Evan. And I totally appreciate that more and more of you are putting pictures. It really does help a lot. Thank you so much. And good afternoon, Jacob. Thank you. And more and more you're showing video like at random moments. It helps so much. Really, it just makes it a livable experience for all of us. And it's not meant, but blah, blah, blah. All right, I think you all get it. So thank you. Hello. If I didn't say hello to someone, I apologize. Oh, good afternoon, Janine. Thank you. I apologize. I didn't say hello to you. Okay, cool, cool, cool. All right. So now we do have this exam coming up. You might have just seen that I did just post something that is meant to be helpful for it. I'm not going to spend all day talking about that document. I'm going to spend some of today So what I just posted, actually, maybe someone should confirm. Hopefully you saw like about 10 minutes ago that I posted a practice. Yes. Okay, great. Thank you, Antonio. All right, awesome. That totally counts as a million points. And thank you, Shankia. That totally counts. That counts as participation and it counts as closing a conversation for whatever it's worth. And people are getting so good at that, I'll probably have to put another portal for that. Oh, more people coming. Sorry. But all right, so that thing that I posted, I'm not going to explicitly pull it up right now. We will get to it, but let me just try to give you an overview of the deal of the purpose of that document. Your exam, well, first of all, that's kind of like the instructions and it's like the instructions and the formatting and everything about what you should expect when your exam gets posted. Your actual exam, midterm exam, will get posted no later than 7 p.m. this Thursday, possibly a little bit earlier, but no later. So wait, I'm seeing something in the direct chat. Yeah, totally. Okay. So the question in the direct chat. Yeah. Okay, that's exactly what I'm about to address. All right. So in the direct chat, I'm being asked, is this document supposed to reflect the upcoming midterm? How does it compare? Good question. That's exactly what I'm here to tell you all. And it kind of tries to say it in the instructions, in the Google Classroom instructions. But here's the deal. Your actual exam that will be posted Thursday night will look identically, almost identically to a significant portion of this practice. That is to say, let me be as clear as I can. This practice is longer than your actual exam on purpose. This practice contains everything that could possibly be on your actual exam. There will be nothing on your actual exam that does not appear somewhere in this document. So in other words, to get to the chase, if you knew this document perfectly, there's no question you would know your midterm perfectly. And I literally mean that. Your midterm will be a subset of this document. Some places I will change numbers, things like I will change details here and there so that you actually have to think when you're doing yours. But I mean like details and I mean like numbers. And some places I won't change anything at all. I'll be more clear about that in a moment too. But what I'm saying, the main change between this thing and your actual midterm is that your actual midterm will be shorter. That might, and I'll tell you how much shorter, you'll notice if you look through this thing, if I did it correctly, this thing is worth 140 points. Like it has 5 problems that all together somehow add up to 140 points. Your actual midterm will be 100 points. This thing is like 5 problems long, I believe. Your actual midterm will be 3 problems long. Either that means I'm just literally taking 3 out of these and making it your midterm, or possibly it means I'm taking 4 and giving you a choice, like something like that. You will have to do 3 problems on your midterm. The 3 problems that you have to do will be taken from this set of 5. Okay. It's kind of like if you were ever on a cross-country team, for example. It's kind of like how if you're on a cross-country team, you take like 10-mile runs during the week to practice, and then your actual race on Sunday is a 3-mile race. Like, obviously, that's a dumb analogy, but that's the philosophy here. This midterm is deliberately longer. It covers all the possible material that could be on yours. Your actual thing will not take as long as this. If you know everything in here, you are good to go. And I mean that explicitly. Like at most, I'll change numbers and small details here and there, but like your midterm will basically to write, the way I do this is to write your midterm. I'm going to take out this document, and then I'm just going to go through and alter certain details, and maybe even fix certain errors, and I'll eliminate certain problems, or I'll say, choose this problem or that problem. But your midterm is just excerpted from this practice document. Okay. You will, and we are going to, and if you look at it, you'll see that you recognize some stuff already and some stuff you don't recognize. We're going to have addressed everything in here by the end of tomorrow. Like we have all of today, and we still have tomorrow. Those are long classes. We will have addressed one way or another everything in this midterm. Some things are really old news. You'll see at the beginning. Some things are like kind of old news at this point, hopefully, and some things at the end look kind of hard and super new. We still have 5 hours to get to them. This is where I've been saying the summer course, we get faster and faster in this course. But so in other words, the end of this whole practice midterm reflects like homework 4, which we haven't talked about yet, but we will have to talk about by the end of today and tomorrow. And we will. Oh, yes, go. Sorry. Yes.
Well, we're going to get a practice midterm first, and then the actual midterm like last semester.
Well, that's what this is. This is the practice midterm. That's what I'm saying. A good question. But so this is the practice midterm, the actual, and hold on, I see the question in the chat. I'll address that in a second. But yeah, so this is the practice. Totally good question. Let me back up to everybody. This is the practice. Again, it's not meant to be a trick. It totally is the midterm, only it's longer than the midterm. If you look at problem 1 of this, so it's like 5 long homework assignments in effect. The very first one, hopefully you'll see, bears a lot of resemblance to what we've been talking about in class. And then the second one bears a lot of resemblance to what you've been doing in lab. The third one is homework 3. I believe it's the fourth one is homework 3. And you're going to see today that homework 3 is a lot easier. Like if you've been okay with homework 2, let me back up. Well, hold on. Sorry. So this is the practice midterm. Some of this you already have answers to, whether you realize it or not. Some of it I will explicitly give you answers to by the time you have your exam. Some of it I will actually post actual solutions, but some of it I won't. But that's because I'm telling you right now what the questions are. You're going to have, so between today and tomorrow and Thursday night, you'll have this much lead time to see what you understand, what you don't, what you have to figure out and all of that. And then Thursday, I'll post the actual thing, and you'll have till Monday 1:15 to do the actual thing. The actual thing will look remarkably like this. This is the thing we're going to talk about for the next 2 days to get you ramped up or amped up, whatever. And again, just to remind everybody, not to go off the topic, but once I post the actual thing Thursday night, you have open universe to do it. Open universe. I mean, that means open book, open Google, open Wikipedia, open Khan Academy, open 3 Brown, 1 Blue, whatever, open YouTube, open class notes, open colleagues. And I'm not exaggerating. I mean, I'll reinforce this, but so to stay in control, to answer Ajia's question, this is the practice. It's practice in that it's an advanced look at the actual thing. I will give you some solutions to this, but some I'm just going to give you by talking through class notes today. You'll have to pay attention. Some I'll actually post some I won't. Anything that I don't, any part of this practice. Okay, here's the real direct answer to Ajia's question also. Anything on this practice, any question on this practice that I don't literally give you an actual solution to or something, or post an actual solution, that's a guarantee that if you see, that means one of two things. Either it won't appear on your actual thing, not likely, or it means that when it appears on your actual thing, it'll be verbatim exactly as you're seeing it now. So you can consider this like, in that sense, like a research paper or a research project. Like if I don't give you a solution to a question on this practice, that means it's because you're totally going to be asked that exact question on your take-home midterm that's posted Thursday. So, this just gives you 2 more days to figure it out or practice or ask questions. Okay, and last thing to say to Ajia's question, the other sense in which this is practice is like, even though this course, even though we move fast in a way and it's summer, all that, tonight you can take as much time as you want to look through this whole thing and see where you're freaked out or where you're not freaked out. And any questions you have about it come tomorrow. Like granted, that's only 1 day, but it is a double period and it is the way summer works. So and I will answer questions tomorrow. I will, like, hopefully I'm just going to get to a ton of stuff in my own way, but any questions you have on this thing, I will do my best to answer tomorrow. And then again, what's going to be on the real thing posted Thursday will be nothing but stuff from this document. So this document is like, yeah, it's the practice or it's the rough draft for your actual exam, however you want to say. And in your actual exam, you're going to approach it just like homework. Like the more steps you can give me, the more explanation you can give me, the more thoroughness. That's what we're looking for. The point of your exam is not just to give me correct answers, because I already know the correct answers and I know that you have them because you can go all over the web and get them, blah, blah. The point of your exam is to show me that you understand why the correct answers are correct. In other words, your exam is a proof. It's a proof that the physics works. It's a proof of every individual item of physics, and it's a proof that you actually get the proofs. Okay, so this is the practice exam. Lastly, sorry, in the chat, there's a lot in the chat now. The first question in the chat, I think, was about extra credit. Hold on a second. Oh, yeah. Okay, well, sorry. Okay, right, and fair enough. Again, about the extra credit, I know someone asked about this yesterday. It might be the same person. I can't remember. I do believe in the extra credit. I will somehow or other there will be extra credit. That's another. So somehow or other there will be, but if I tell you in advance what it is, I'm not sure it's the same kind of extra credit thing. But one example of how, so I will do extra credit. It might be different from Walter's in that I might end up giving you the extra credit after you turn in the exams and I see them and I'm like, oh my God, everybody messed up over here. I'm now going to make an opportunity for extra credit points on a similar topic. So it might be after, or maybe even more likely. What I'm trying to say to everybody is your exam will be 3 problems long, whereas this practice is 5 problems long, right? Like, so either I'm going to eliminate 1 problem or 2 problems, or you're going to get a choice or something. What I might do, what could happen is I might make your exam 3 problems long and then say for extra credit, do this 4th problem. Oh, but taken from the practice I just gave you. Like that's, so I'm not going to tell you in advance how I'm going to do extra credit. Somehow or other there will be, I promise. I didn't explicitly make it clear in the practice that there is, but there will be somehow or other. So that's one. Oh, one question. Yeah. Oh, wait. So I'm sorry. I'm looking at all the private chat stuff. Yeah. Okay. Some of the direct chats are kind of funny. Okay. One thing before I forget, when the exam, so hopefully, so as far as instructions, I think hopefully they're sort of clear in the Google Classroom posting of this, like not in the document itself, but in the assignment instructions, the actual exam. Yeah, okay. That's a great question, Shakia, and thank you for making it public. It is a little easy to the extent that you guys can make these things public. It is a little bit easier for all of us, I think. So, okay, wait. So let me answer Shakia's question first, since it's public, and thank you. The answer to her question is, would I like you to submit the practice exam to me? And the answer is no. I mean, totally fair question, totally legitimate question. And please, everybody, take a moment when you're not stressed or when you're not in the class to sort of carefully read the instructions that I put in the Google Classroom thing. But no, the practice is 100% practice. It is 100% for you. It's 100% to try to keep me on track, to show me what I got to finish in class before you take your exam. I don't want your practice. Oh, and I guess it is confusing because I put it in the assignment portal. Okay, that is confusing. I should have put it in the material portal. If I can change that, I will. Oh, I see why that is confusing. I don't want it though. That's my bad. Okay. I don't want your practice. The practice is for you. I don't want to grade it. I don't want you to rush it to me. I don't want to give it back to you. Okay. I think it's in the wrong portal. I think that's why that's confusing. Don't give me your practice work. It's for you. But it is a promise from me to you that your actual midterm will not be a surprise at all if you go through this whole practice. Okay. That's number one. I want to look at that portal for number two. I'm being asked in the direct chat, when's the actual exam due? The actual exam will be due a minute before class. Oh, sorry. Oh, cool. Thank you for the closing this in. Okay, wait. So there's a lot happening in the chat. One thing, wait, let me pause for a second because actually hold on. That question about submitting it, I never realized before why that was. Let me see if I can quickly change that because that is confusing. Hold on, I may not be able to. It may be too late. Oh, well, okay. So it doesn't say. It doesn't actually. All right. So the practice, I sort of did it right. I mean, it is. Oh, it is in material. Oh, okay, okay. It is, yeah. So you couldn't submit. Here's the deal. It's still a fair question. I'm not saying it's not a fair question, but look, to everybody, I'm going to try to answer these questions in the chat. I mean, they're all fair. And of course, we're all anxious about exams. But just please know that there's actually a lot of clear instructions be right in the posting, the Google Classroom posting. Maybe it's like not so easy to read on devices, but it's there. So you'll notice one thing is you couldn't submit this thing if you tried. Like it's actually technically called material, not an assignment. It doesn't even have a point value. There isn't a place for you to submit it, and that's on purpose. The actual exam will be posted like an assignment. It will actually be worth 100 points. And to answer somebody's question, you will have to submit the actual thing right before class on Monday. Like it'll be due 1:15 p.m. Monday, and then you show up to class. And it totally does say this, and I have to be explicit about this. You've got to submit it at 1:15 Monday, unless you've talked to me in advance because of some extenuating circumstances, and then you got to show up to class. Frankly, after you sit through class, if your head is spinning and you had such a horrible weekend with the whole thing, blah, blah, and then you have to phase out or something, like we're human beings, I get it. But I really think that it's important for each person to see all their colleagues show up at the same time they did after they've suffered through the exam. I really think you want to look around at 1:15 and see that all your friends or whatever, your people are there and they've suffered the same way as you and they got the exam in as well. If any of you guys see someone showing up 45 minutes later and then popping the exam into the portal, like you're going to resent that person and justifiably. Right. So it's due, to answer the question, the actual thing will be posted Thursday evening and will be due Monday afternoon, right before class. This practice thing is never due at all. It's just for practice. My phone number, I'm also being asked by the chat. I'm going to put it back. I'm going to put my phone number in the chat right now. That's another question in the chat. Wait, sorry. Oh, thank you for saying, okay. Wait, oh yeah. And then there's another question. Okay. Hold on one sec. Hold on. Okay. If anybody runs into any issues at all about the exam, yes, thank you for asking nicely. In like 3 minutes, give me 3 minutes. So I just put my phone number again in the chat. Someone asked for it, and I totally understand. And anybody who, I'll just say this publicly, if you had it last semester, but then you intentionally deleted it so you didn't like accidentally call me, I totally appreciate that. Yes, I totally understand and I appreciate it. But so there's my phone number again. You totally can use it, especially if there's a time urgency thing. It's probably easier than email in some ways. The deal, I don't mind if there's a question about the exam, either a question about, I mean, especially like in the, whatever, if there's a question about the exam, whether it's because you have an issue and you need to clear with me, like I'm about to go to the hospital, I can't turn it in on time, or question number 3, I think this is a typo, whatever, you can text me. You should text me. Excuse me. You should text me, especially if we both think that that's going to keep things fast and short. But that's the deal. When you text me, you, anybody who, I mean, whether you're the person asking, anybody, you can text me. But certainly identify yourself first if you're at all unsure whether we've ever texted, before. But second of all, you've got to ask me short answer questions. Like whatever it is that you want to find out from me, you've got to phrase it in a way that I can either be like, yes, or I can be like, no, or I can be like, no, the minus sign is supposed to be there, or give me choices. Like, is it velocity or acceleration? Don't text me and say, can you please teach me harmonic oscillation? Do you know what I'm saying? Like, that's just unfair to both of us. That's not how texting works, right? The point of texting is that if you feel that I can answer your question quickly, then that's to both of our benefits, and do it. But if I have to take more time answering the question than you took to construct the question, that's not fair to either one of us, and it won't help you. Like if I start giving you paragraphs and paragraphs in the text, like trying to rebuild the concept of harmonic oscillation so that you can learn it for the first time in the middle of the exam, honestly, it's not even going to work for you, right? So please do feel free to text me. As long as you can give me a question that takes me less time to answer than it took you to write, then we're both good. And I'd be delighted to do it. And it could be 5 of them. I mean, some people last semester did text me a lot, but every time they texted me, they were like, is this supposed to be a 5 or a 7? Or they're like, is question 3 a typo? Or are you sure? And if it's like that, great. Then we both feel like we're both doing our job. Okay, so that's my phone number. There was another question. Oh, another question in the chat. And of course, I do want to get to the material. Oh, and then I have to pause for a second. Another question in the chat, and then I'm going to pause for a second, was another question in the chat was, did I say I expect you to show your work? How do I expect you to do that? Okay. Now that's a very important question. That's a very kind of broad question. It is true. I totally expect you to show your work, especially on an exam. My fast answer of how to do that is whatever you feel like I've been rewarding you on homework is what I want. And whatever I've been criticizing you on homework is what I don't want. Like I want the more explanation, the better. Another way to put it is, in fact, let me back up. This addresses some other things. You're going to see in the practice exam just looks like a bunch of homeworks pasted together. I mean, and that's what the exam looks like. It's like 5 long or the actual exam is like 3 long problems. You're going to solve them the way you do homework. That is, you're going to take out separate blank paper. I probably should have put that in the instructions, but just like homework, hold on. Sorry. Yeah. Wait, no. So, right. So someone just asked in the direct chat, do I want you to submit the exam answers in the format of the homework? And then they wrote, like, I hope that question makes sense. Yeah, that question makes sense. Yeah, that's totally what I'm trying to say. Like, the homework has been meant as like practice for this experience. You want to treat the exam as just like a super serious, super involved, super counting version of what you've been trying to do on the homework. Absolutely, yes, direct chat person, like good question. So what that really means is you're going to take out separate white paper, or separate blank pieces of paper. You're going to treat them like a blue book. Like you're on separate pieces of paper. You're going to number the questions. You're going to indicate to me what question you're on. You're not going to cut and paste the whole question. But you're going to say like question 1, part A, and then you're going to say like given, pendulum or whatever. You're going to draw a diagram, and you're going to say determine angular velocity or whatever. Determine velocity at moment 3, and then you're going to show me all this work, and you're going to circle the final answer, totally like the homework and totally like a blue book. And when you've done everything and put it all together on blank pieces of paper that are all nicely put together, compiled into one document, you're going to upload it to Google Classroom just as though it's just a regular assignment, only it's going to count actually as an exam. Yeah, you want to show as much work as possible. You want to draw diagrams as much as possible. You want to give me as much English as you can. You want to take whatever, like the best things that you've done on homework and use that as a starting point and go to town. Like if you can use more colors, great. You want to give me a document that I can literally take out, that I can take out your doc. This is true for everybody. I mean, and this is, I really feel like this is great practice for physics research, for science research, for life. Right? Diagrams are required. Yes. Sometimes I'll remember to tell you, but yes, you want diagrams. Like this, I don't mean to sound angry, but yes, I'm looking at the direct chat. Diagrams are crucial. And put another way, like what's required is as much as you can possibly give me. The more you can give me, the more points you get. And think of it as a physics report, if you like, or a physics presentation, if you like, or like mini poster thing, like as in for a scientific, as in for a symposium or a fair or whatever. Think of it as, just remember the main standard. The best way for you to judge your own work, if assuming you're taking pride in it, assuming you're trying to get an A, assuming you give yourself enough time and space to take this seriously, you're trying to give me a document that I could just take your document and start opening it. And that I'm a guy who knows physics, right? You're assuming your audience knows physics, but just that, just assume your audience knows physics, maybe even likes physics. I assume that I don't have the actual exam in front of me. Assume that I just have your document and I'm just opening it up and I'm reading for physics. You're going to guide me. You're going to show me each question, what the question is, and guide me from the question to the ultimate answer so that I can, so you're actually telling me the full physics story on each question, and I shouldn't need anything else in order to judge whether that's a good physics story or not. Whether, I don't mean story like fake, but I mean like physics report. I should just look at your document and be able to judge whether it's making physics sense and going from beginning to end on each problem. Again, you can assume that I know physics, but just assume that. Don't assume that I know anything else. Don't assume that I know what the questions are. Don't assume that I know what's inside your head or that I've ever met you before. You're giving me a physics presentation that's trying to, in as much detail, walk me through first principles and questions to final answers. So you're trying to prove the physics and you're trying to prove that you actually understand it. Like, so the more, so in some ways, there's a lot of judgment calls here. So let me back up for a second, then I'll get the chat and I'm gonna take a break for a second. Like in some ways, this is an easier, less stressful job than many others you've had in science classes. Like, because again, I'm saying you have from Thursday to Monday to do this, open everything. You can talk to each other about it. You can help each other. That is not cheating. I'm actually encouraging it. You can also talk to your aunt who happens to be like a Nobel Prize winning physicist in Stony Brook. Like you can, and you can totally go on Khan Academy. I'm saying you can do all of that. And you should try to do whatever you need to learn the physics of this thing. And I'm not trying to play hide the ball and surprise you with what the physics is. You know what the physics questions are. But remember, so the good news is that you can use whatever resources you want and take as much time as you want to get from beginning to end on this document. That's the good news. The bad news is, remember that I know that. Like, I know that I'm telling you that. So that what I'm looking for when you give me the document is I'm not just looking for the correct answers, because like anybody can get the correct answers off the web. I'm looking for you to demonstrate to me that with all of this time that you've put in the class and in your research and in the week, with talking to your friends, with talking to your aunt, whatever, that by the time you get to that piece of paper, you actually get what you're talking about. And that's what you're trying to show me in the paper. And I can tell the difference, believe. So it's kind of the simplest job ever. You're in a way spitting back to me physics arguments that we will have already made together and that are not going to be a surprise. But that's what's simple about it. What's not easy is you've got to actually show me that you understand your arguments. So you might want to think of this more as a physics research presentation, if you like. I mean, presentation matters. The more neatly and clearly, the more you can make it easy for me to look at and go through and see that you know what you're talking about, the better for both of us. You're trying to convince me that you get this physics. That's the bottom line. Let me just, wait. So in some ways, I can't explain it better than that, but it's all about you doing everything you can to explain to me that you know it, which also means parts that you understand, go to town. If you think something's easy, add a lot of extra steps. I mean, this is a mistake that people make all the time. If you think something is easy in there, if you're like, well, duh, well, then if you think it's duh, don't just be like, well, duh, it's one step and then move on. If you think it's duh, expand, show me why it's so obvious, explain why, like earn a lot of points there. Go to town on the places that you think are straightforward. Just because they're clear to you doesn't mean that you can't break. The clearer it is to you, the more you should be able to break it down and explain why it makes sense. But then the parts that are harder, well, you've got time, try to figure them out. But the more you can break things down into steps, the better. Even if it's a point where sometimes you say, I don't understand this step. If you can even be honest about a certain step, okay. But don't just copy things off the web, because I do know the difference. But okay, wait, quick chat. I want to look in the chat, and then I want to give my son something, and then, oh, I guess I answered this. So diagrams. So in a way, like nothing is literally required, but everything's required. The more diagrams you can give, the more English you can give, the more colors you can give, the more neat, like handwriting is not required. Like I can't grade you on handwriting, but I'm telling you right now, if you make your handwriting clear and you make it easier for me to read, of course it's going to do better. It's like a presentation. I'm going to pause for 1 second. Excuse me. You want the robots? Robots? You want? Oh, no. Well, I can only do it. It's just an option. But did you set it up? I can't. Is it ready to go? It would make it ready to go. Like, well, I'll buy you what I can. I know. Well, so get me. Oh, wait. You're going to buy 400. Okay, sorry about that. All right, hopefully this is getting clear. No, everything I'm saying is not. Wait, what? I did buy you 400. I just bought you 400. Yeah. Okay. If you want extra credit, like then learn how to play Pokemon Sword, get a Mewtwo, and talk to me about trading for my son. No, that's a total joke. Okay. Okay. So we're going to go to material in a second. Hope again, none of the, it's all designed like an A should be within everybody's grasp. But yes, it will take work. Like this is the exam is funny this way. Like there's no tricks, but it is tricky. Okay, I want to get. I think I want to. All right, you will notice. All right, I want to quickly progress to a couple more. I want to quickly progress through the rest of homework 2. We spent a lot of time yesterday on one particular question, homework 2, that got us into phase, that got us into angular velocity. You're going to see how that totally, I believe that if you've been paying attention, even if you didn't understand homework 2 at first at all, which is fine, if you feel like you're understanding so far what we've been doing with homework 2, which is very fine, I think you really will understand homework 3. You will see that homework 3 is not hard at all. And we're going to show you that today. And you'll see that homework 3 itself, literally a cleaned up version of it, is one of the problems on the exam, like on the practice exam, homework 3 itself. And we will nail it today without a problem. So that'll be another problem on the exam that will be done and over, and you'll have answers to definitely by the end of today. What am I trying to say? Again, I guess the last, we're not, I didn't say that clearly. We're not done with homework 2. I still want to go back. I want to go back to it right now and do a couple more things with homework 2. And then we're going to move to homework 3. I will say this, as long as someone just asked in the private chat. Oh, okay. No, cool. Thank you. And that totally counts as closing the conversational circle. But let me actually, but that's a fair question. We're about to go back to homework 2 right now. There are parts of homework 2. There's a whole section about vectors that's important for later, but it's important for later. And I'm glad anybody who did it got a lot of points and all that. But to be clear right now, the whole section of vectors that's in homework 2 is not part of this midterm exam. Like, you won't be tested on it. So I'm not actually going to go over that today. Like, I'm going to do a little bit more of homework 2, and then I'm going to go straight to homework 3. And that whole part of, if you're hearing me right now, the whole section of vectors that's on homework 2, first of all, you can still hand in later for points. It's not dead or anything like that, but you're not being tested on it. You won't find it anywhere in the practice midterm. That's intentional. So I'm not even going to worry about it today. Okay. And that goes for any other material. Like, anything that's not in the practice midterm is not on your midterm. Anything that's not in the practice midterm is not on your midterm. So all I'm worried about is getting through my version of any material that I put in your practice midterm. That said, I'm going to go back to homework 2 now to finish up some aspects of it. And then we'll go to homework 3. And then we still have tomorrow to go over homework 4. Okay, so bear with me for a moment. People are coming in and out. Okay, sorry, just trying to get back to homework 2 here. Okay, homework 2. So we spent a long time on 1G yesterday. I'm now going to go to H, hopefully do it a little bit quicker, because H we've said things about. For H, okay, anyway, I'm going to go to homework 2H. Okay, so we're going back to part 1, letter G of homework 2. I just want to say again, as you see in the notes here, part 3, I'm not even going to talk about today or tomorrow because it will not be on your midterm. It is important in life. It's just not important right now. So just to be as clear as possible about that. So I'm sorry, we did letter G yesterday. We're doing letter H now. Okay, so letter H is. Okay, now this hopefully I'm going to go a little faster. Again, just a random function was just introduced here. Like someone just like, this is like a math thing. You're walking through the math forest and someone just like walked up to you and said, I got this function right here. X equals e to the negative omega t. Can you take a derivative for me? And you're like, okay, I'll take a derivative. Like, it's not immediately obvious why this does or does not have anything to do with our physics, except remember sidebar 1 and sidebar 2, where we on purpose looked at both trigonometric, but also exponential functions. We looked at exponential functions because we noticed that when we take the derivatives of exponential functions, we get back exponential functions. So there's something about exponential functions that suggests they might be good, appropriate functions to you? Yes, very nice. I love it. When I just saw that someone in the direct chat just wrote the beloved chain rule. That's awesome and totally correct, I might add. Yes, that's awesome. And that you should totally submit that for 85,100,000 points. Yeah, so we're totally going to have to use the chain rule here. We are, and we're going to use the chain rule on an exponential function. And we're going to remember that the thing about exponential functions is that they return themselves as derivatives. That's why they're even coming up at all, because this whole course right now is about that concept, about something whose rate of change returns itself. Right, which, by the way, is another fancy way of saying feedback. Really what we're looking at in all this, ultimately, the physics and the math that we're looking at is feedback, where a cause produces an effect and the effect becomes a cause that produces that effect again. Hence, okay, so all right. So, well, okay, so the answer, so thank you, direct chat person, right. I mean, so the answer is, okay, that's the answer to that question. Oh, sorry, so I should circle it. And I'm trying always in my solutions, I'm always trying to give you a model in my solutions of what more or less I'm expecting you to do on the exam, right? Notice I labeled where we are, but so I wrote that it's like homework 2 part 1 so that we know that's me and you talking as teacher and student. But then literally, even if you don't see the H and you don't see the part 1, I wrote given X equals blah, blah, blah. And then I wrote the question dx dt equals blah. Like anybody could follow this, even if they don't have homework 2 next to them. That's the point, right? And ideally, maybe I even should have written a diagram, but this is so pure mathy that I didn't. So I circled the answer. Now, let me also explain why that's the answer. And if this were your exam, you would probably do what I'm about to do, like give an explanation. But then if the same problem type is asked like 4 times, you don't have to give the same explanation 4 times. You can say, see explanation above, right? Like in other words, the very first time you introduce the chain rule, explain it. But then after that, you can always say, okay, where, it's so funny, I'm getting in the direct chat. So I'll just finish my sentence. Well, here we go. All right. But yeah, so if you were taking the exam, you would, anytime you do something for the first time, break it down and explain it as much as possible. Assume there are a bunch of people watching you with direct chat functions who are going to grill you with questions. But then once you've explained it once, you can refer to it later on in the document. So the answer, so in the direct chat, someone just asked, where did the negative omega come from? And the answer is the very thing that someone else said in the direct chat, which is the chain rule. But here, I'll show you. So that is the answer, but let me show you, because okay, so I'm running out of space here. I'm going to do this on the next. But so the first thing I'm saying is, I'm just reminding you to answer both questions. Anytime we have an e to the blah, the derivative of it is e to the blah, right? So that, but I know that part the person understood in the chat. But what we don't just have an e to the blah here. We don't just have e to the t. We have e to the some function of t. And the chain rule says that when you have a function of a function, the derivative of the whole thing is the derivative of the outer times the derivative of the inner, right? And the inner function here, like the inner function is negative omega t. The derivative of that with respect to t is negative omega. Like I'm saying that in English, but I'll write it down. So all I've justified in red right here is where the e part came from. But now, so you can tell me if you need to go back to the last page. Well, actually, I'll stay in red. Sorry. right? Like what I'm trying to say here with chain rule is we have a function of a function. We have x equals e to the t, but it's not just e to the t, it's e to the t. What do I mean by that's what I'm calling z, some function of t, specifically here negative omega t. So right, the outer function is e to the z, the inner function is z equals negative omega t. So we do the derivative of the outer times the derivative of the inner. I don't know if I can explain it much better than that. So we multiply our whole answer by negative omega because that is the derivative of the inner function. I hope that makes sense to the person that asked in the direct chat, but that, well, we'll see. But so the answer to the first derivative is negative omega times e to the negative omega t. That's the first derivative. Now, bless you. Now you'll see maybe if it makes sense or not, like in a way just now practice, but also a conceptual next step is we're asked to do the second derivative, right? The second derivative. And again, you tell me, I'm just flipping through pages now. Tell me if you want me to. The function that we're dealing with is still that. We got the first derivative. The function we're dealing with is still this. We got the first derivative, which is this. So we want to take the derivative of that, and you'll know that you really do know what's going on if you say, oh, okay. Well, chain rule again, the negative omega comes out again. So we get, if you like, negative omega times negative omega times e to the negative omega t. Well, negative omega times negative omega is positive omega squared, right? I mean, negative times a negative is a positive, and omega times omega is omega squared. So we get omega squared e to the negative omega t. That's the second derivative. And that's the answer to that question. You can stop me in the, and hopefully in the person in the, well, okay. Right, so that's the second derivative, and that's all the sheet is asking for, I think. Oh, right, that's all the sheet is asking for there in part H, but now we go to part I, which is the point of the whole thing. Like this would just be random math if it weren't for this question. I is in effect is following from H. It's like thus is. It's sort of now this is why anybody introduced that E function in the first place. It goes back to our first week of school. We're like conjecturing possible solutions to the differential equation, which is a mathematical way of saying we're trying to come up with different models of how can you predict where a mass is at any given moment if it's going back and forth on a spring, or predict where a pendulum bob is going to be at any given moment if it's going back and forth on a string. Like these different functions are attempts to model or predict the space-time behavior of some system. And what we know about the system is the differential equation, because that's just a mathematically fancy way of saying Hooke's law. So someone guessed the E function because it was a reasonable guess. Now we differentiated it twice to see whether that was actually a correct guess. Is x equals e to the negative t a solution to this thing. In fact, I should do that in a different color. Like that is it seems random. Like we're just taking derivatives and it's like, oh, is this a solution to that random thing? But it's not random. The question always at this stage of our life is anything we're looking at a solution to this? And this is Hooke's law. This is simple harmonic oscillation differential equation. It doesn't have to be x's. It could be y's. It could be z's. It could be thetas. As long as you were saying the second time derivative of the variable is directly proportional to the variable itself with a negative sign, then that's the system we're talking about. So is it a solution to that? Very good question. And the answer, so that's an important question. The answer to this, to part I of part 1 of homework 2, the answer to I is no, it is not. Now, some people most people got this right on the homework, which is cool. And again, if you still haven't handed in the homework, you still can. I don't care that I'm going over it right now. But some people did get this wrong. So let's just be careful about it for a second. Like when we took, so let me write, the answer is no, it's not. And that doesn't mean it's a false question or a trick question, or it doesn't mean that all your work is in vain. It means we just discovered something. It means that that conjecture is a reasonable, but ultimately false conjecture. It's just like our experiment just worked out to that result. No, not a solution. And the reason it's not a solution, well, I'll go to the next page. Well, the reason it's not a solution is because the conjecture was that x equals e to the negative. Excuse me, the conjecture was that x equals positive e to the negative omega t. And the question is, if you differentiate that twice, do you get negative omega squared times itself? You don't. You get positive omega. That's supposed to be a positive sign. Like it's super close is what I'm trying to say. Conceptually, when we differentiated this twice, we got something that looked very, very much like the harmonic oscillation equation, but it's missing the negative sign. And that is a big enough deal to say no. In other words, it's like saying, in effect, that if you pick that E function, which has a lot of nice properties and looks like it's going to work, but if you differentiate it twice, in effect, you end up getting something that looks like f equals positive kx, not f equals negative kx. And that negative makes all the difference. If you just go back and think about springs, the whole idea of a spring, about elasticity or about oscillation, the whole idea is that you pull a spring to the right, it pulls back to the left. A spring restores. It's a conservative force because it's a restoring force, always bringing you back to equilibrium. If a spring were to push in the same direction as you pull it, that's totally not elasticity. That's some weird superpower. I mean, that'd be cool, but that'd be some totally other thing. Maybe like a proton-proton repulsion or something. Okay, so this is not harmonic oscillation. This does not satisfy the differential equation 100% because the negative sign doesn't work out. That's how important negative signs can be. Okay, so the answer is no. I'm going to just keep going. As you can see, I'm going a little faster. The faster I go just means the faster I'm going when no one's saying anything. Please, you can still stop me. Maybe you have to stop me even more if I go faster. I will take questions in the chat. I will. I'm going to go this fast and faster until I get those questions. Okay. So I'm just going to assume you're all cool and I'm going to move on. But I'm not saying you shouldn't be uncool. I'm not saying you can't ask questions. I'm just saying if you don't, I'm going to keep going. Okay. So that did not satisfy the differential equation. Let me just look in the sheet for a second. Sorry. Okay. Okay. I'm going to insert something really fast here. So that was I. I want to go to J. I'll get J. Oh, wait a minute. Yeah, I want to go to J and K. They might look intimidating to you. Don't be intimidated by them. But even before I go to I and J, I'm going to insert hopefully a super quick sidebar here to really make the point. Notice I'm saying the E function was a good idea. It certainly captures something important in physics and math, but it didn't quite capture oscillation because the negative signs didn't work out. Another physical way of saying this, by the way, is remember, we're talking about oscillation. We're talking about something that goes back and forth, back and forth, back and forth with like a frequency and a period and cyclically, all that. You know, cosine functions and sine functions do that. They go back and forth, back and forth, back and forth. Exponential functions like exponential growth and exponential decay, they go up monotonically forever, or they go down monotonically forever. Like they look very different. If you just think of the graphs, it's actually not surprising that an exponential function is not an appropriate description of a mass on a spring, because like it would be more of a description of a mass that just like rocketed off forever. Okay. So it was a good guess, but it's not shocking that it didn't work out. Someone's here. Sorry. Okay. But mathematically, what didn't work was the negative sign. So what you might say, so that was part I, right? That was part. So, right.
Did you want the grilled cheese or no? Should I heat it up or? Okay. Do you like your new toys? Good.
Okay. This is all what you can consider sidebar 4. It should be quick, but if you're following the logic of this whole narrative, and hopefully you do see it as a narrative, and hopefully you do see it as logical, I'm saying that E was a really good guess, but it didn't work out because of a minus sign. So if you're following this, it's really reasonable in your head to say, well, wait, okay, if it didn't work because of a minus sign, can't I like put in a minus sign to fix that problem? I mean, a minus times a minus is a positive. In fact, I remember someone asked on the third day of class, I think it was Shakia, it might have been Juanita. Somebody asked somewhere when we took the derivative of cosine, we got negative sine, and then we took the derivative of negative sine, and like we still had negative cosine, and somebody very intelligent, one of those two people, I think, and I don't mean to confuse it, it was a 3-syllable name, I know that. Somebody said like, wait, you know, isn't a negative times a negative a positive, which is a totally reasonable thing to track, right? And a totally reasonable thing to ask. We could ask that right now. Oh, sorry, was it? Oh, now I'm afraid. And I totally mean this as a compliment, like, and it comes up now. Like, if you're following this now, what I'm saying is we're off by just a negative sign. So it's totally reasonable to be like, well, if we're just off by a minus sign and everything else was cool, can't we compensate like by introducing a minus sign? And it's very reasonable to think of these things. And oh, cool. Yay. And I feel better. Thank you for thank you. I'm going to open up a portal for that type of thing. I don't know what that type of thing is, but thank you. Yes, it totally was, Juanita. Awesome. And it was awesome. And I want to dwell on it now, first of all, because I'm going to do it for a second as a sidebar right now. Like right now, that is physicist thinking. Everybody, it's very easy to confuse, like to think that what it means to be a physicist is to have physics answers. No, it means to ask physics questions, right? And science isn't about science conclusions, it's about a scientific method. So anytime like we think we're sort of getting something, but then we're like, but wait, what about this thing over here? It's way too easy for us to think, oh, I guess I don't get it. I guess I'm the problem. I'm an idiot, whatever. No, if we go like, wait, what about this thing over here? Then we're actually doing science, right? And we got to stop and honor those, wait, what about this thing over here? Ideally, we honor them around and up and through and to an exam. And ideally, in the middle of an exam, we finally have enough confidence that we're okay. But even this exam, you have all the time, it's take home. So wherever it is, if you have a moment like that where you're like, wait, but what about this thing over here? Trust it. Trust that it means you're smart, not stupid, and follow that reasoning. So because you'll discover something. So that's what I'm going to do right now. I'm going to say, wait a second. If the problem is a minus sign, can't I try to correct the problem by going, so this is a sidebar because it's not on the sheet, but I'm saying sidebar, what did I say? Number 4. I'm saying, what about, and I'm not asking you guys, I mean, I'm showing you, it's like a rhetorical question, but I'm saying, what about x equals negative e to the omega t? Like, that is a really good question. If it's even remotely nagging at any of you, like, I kind of get what he's doing here, but like, wait, why wouldn't he just, yeah, okay, why wouldn't I just put a negative there? Won't that solve the problem? But here's the deal. Here's the deal. And I'm going to do it sort of quickly. If I take a derivative, or maybe you can do even faster to practice. If I take a derivative of this, I'm going to bring down the negative from the omega chain rule. And indeed, it will cross out one of those negative signs, right? So I get that. Then if I do the derivative again, I'm going to take down that omega again. So I'll get negative omega squared e to the omega t. And now that's looking good, right? Because it's looking like, oh, cool. Like, wait. And I'm not trying to trick anybody. I'm trying to follow the reasoning. If I do that, now I have that the second time derivative of x equals negative omega squared e to the negative omega t. That looks a lot better. It almost looks like, yay, we won. We worked it out. We've got a negative sign here. But let's be super careful, like not quite, because the thing is, remember what we just said that x is standing for. X itself is standing for negative e to the negative omega t. So in other words, what we now have is this. And again, I'm not trying to trick anybody, certainly not Juanita, and I'm not trying to trick myself at all. I'm trying to actually follow these things as though I'm thinking about them for the first time, and show you all that all the physicists that came up with this stuff thought about it for the first time as well. They come to conclusions because they go down a lot of roads that are not necessarily right, but they don't know that till they get to the end, and then they back up and go down another road. What I'm saying here is, even if we try to put in a negative sign, that would seem to solve the problem. But oddly, if we're careful, we notice, hold on a second, this whole thing is x. So even that negative sign was still just part of x. So even with the negative sign there, when we took two derivatives, we still unfortunately got rid of it. And we didn't get Hooke's law. We get this positive version of Hooke's law. So no, the exponential still doesn't work. Now, this doesn't mean anybody did anything wrong. This is like a true false question where the answer is false. Like the exponential, what we're showing here is what we're seeing is why we rely so heavily on the cosine function to describe oscillators. The exponential function has a lot of properties that could be good, but it's not quite there. It's off by a negative sign. So exponential is not, still doesn't work. Still doesn't satisfy simple harmonic oscillation. Okay, that was a sidebar. Let me just look at the chat for a second. Sorry. Cool. Thank you again, Juanita. That's awesome. And I'm not kidding. So now I'm going to go back to the sheet, and you're going to see. So now I'm going to go back to the sheet, and we're going to get to the next question, where all of a sudden the imaginary number I is introduced. And if I were you, well, okay, well, let's get to that. But a second, I'm going to move to. So now we're back to the sheet. Back to homework number 2. part one letter, what is this? I think this is letter I, which is a little confusing, I know. Letter, oh no, this is now letter J. Thank goodness, okay. Letter J, so J says given okay, I'm going to pause for a second because I'm going to move my computer, but like this is an attempt. If I were in your position and I'm trying to, and I'm a good person, I'm just trying to do the homework and now I understand, I got the chain rule, I just did the last part 5, and then all of a sudden I get to J, and now just when I think I know what's going on in this class, all of a sudden imaginary numbers are introduced, like what? And I know a lot of you have heard of them, and maybe some of you even have studied them in math classes, but no matter what, I don't think you were expecting an imaginary number to pop up in a physics class. Like, first of all, physics is supposed to be real and imaginary doesn't sound real. Second of all, like, what does it have to do with anything? Like, why would that be here? Well, it's not out of cruelty or out of accident. The reason imaginary numbers are now going to pop up, we're going to try something with imaginary number, is for the same reason imaginary numbers were like invented or discovered in the first place, which is this. We all know a positive times, well, maybe I don't know if I should write this or not, but a positive times a positive is a positive. This is all the Juanita thing. A positive times a positive is a positive. A negative times a negative is a positive. A negative times a positive is a negative, right? Like, I think we all know that. So if you're doing multiplication, if you're squaring things backwards, if you're looking for numbers, so just to remind you, like if I want the square root of 49, that means I want the number such that when you multiply it by itself, you get positive 49, right? So one answer is positive 7. Positive 7 times positive 7 equals 49. But you also know from experience that actually there's another sort of tricky or surprising answer, which is that negative 7 times negative 7 equals 49, because negative times negative also equals positive, right? So if you want the number which multiplied by itself gives you some positive value, you could choose positive or negatives as your square roots. Like, all of you know that. Where it gets weird is like, but what if you want the square root of a negative, right? Like, what number multiplied by itself gives you a negative? And the answer is, at least on the real number line, there is no answer because of what we just said. Like, a negative times a negative is going to equal a positive, and a positive times a positive is going to equal a positive. So there is no real number which, when multiplied by itself, gives you a negative. So we invent, or we discover, this concept of imaginary numbers, and imaginary is like a bad name. I mean, all numbers are imaginary, or no numbers are imaginary. They're all in our head, or they're all in the universe. So it's better to call them complex numbers, as I'm sure you've heard. These numbers, but the simplest version of a complex number is the square root of -1. Like, whatever that is, it doesn't exist on the real number line. There is no positive number that does it. There's no negative number that does it. It's just this other thing that we make up or we discover off the line in the complex plane called I. We just call it I. Notice the triple equal sign. In other words, I'm telling you right now, everything you need to know, anything you need to know about complex numbers for this course, I'm telling you right now, and you already knew it. I stands for whatever quantity is, whatever quantity is that when we multiply it by itself, we get -1. That's what we mean by I. And that's all we need to know about I to figure anything else out that we need, okay? And we're bringing it up now. We're literally raising the idea of I now precisely because we have this issue of, God, we're trying to get rid of a negative sign, but when we do a negative times a negative, we get a positive, and we do a positive times a positive, we get a positive. So we can't, like, how can we get at that negative sign? So we think to ourselves, maybe we could try I, because I is that thing that was invented or discovered in order to address the weirdness of negatives. So that's why I'm going to try it, and I'm just going to try it. And what do I need to know about it? Just what I just wrote, that I, by definition, is the square root of -1. Okay. Oh, specifically there. What does that mean? And I'm going to move in a second. What that really means in terms of calculus is that it's a constant. Like it's just a number that does not change. It maybe is a special interesting number, but it's a number that will not change even under our calculations. So whatever rules apply to constants when we take derivatives will apply to it. I'm going to pause for a second to move my computer. I would ask you all right now, whether you did the homework or not, try right now. Given everything I just said, just assume I is a constant. In other words, it behaves just like omega in the argument of the exponential, in the inner function. Just treat I, don't be intimidated by it, and don't be mystified by it. Just, it's a number, treat it like a number and take the derivative of e to the I omega t. I'm just moving up here right with everybody. Sorry, I'm just gonna move outside.
Okay.
Oh, cool. Right. Oh, it's a really good question. Was this on homework 1 as well? Great question. When we were and thank you, or was that direct? Oh, thank you, Aja. That was not, in the context of homework 1, I totally ended up doing 2 big sidebars, one of which had a lot of information about E. So yes, I don't know if I ever said anything about I before, but hopefully you do. Yeah, but I mean, you're right to say that this is all linked back to homework 1. I mean, that's good. Oh, sorry, I'm just got myself distracted, but definitely all this E stuff. Yes. Okay. So wait, are we all still here? Okay. So, or does anybody want to put the answer in direct or public chat to this? I mean, whether you did the homework or not. And again, even if you didn't do it, you could still hand it in. But if you did do it, it's good practice. Does anybody want to put, so the derivative of e to the I omega t going once? Okay, I'm going to slowly do it just in case anyway. But okay.
I omega e to the I omega t.
Perfect. Beautiful. Yes. 1,000,000 points. Yes, totally. That's awesome. That's Aja Gori, ladies and gentlemen. She'll be here all week. Yes, that's awesome. So I guess I did do this in homework. No, yes, totally. So what she said was, if you couldn't hear, she said, I love physics. No, that's an awful, that's not her. Okay. She said this. Because it is, whoa, is this work? Oh yeah, okay. Whoa, that's weird how it just appeared. Anyway, yes. So she did chain rule on exponential, just like we did 2 minutes ago. Again, this is if nothing else, this is like, consider this all secret, hidden, calculus practice class, right? But we're doing the same skills over and over, but just with things that look more and more intimidating, which by the way, also is the secret of physics. It's always like this. The next step in physics always looks more intimidating because it's always some new factor introduced that you think you don't know. But if you just trust that it's just a detail on something you already know, and you just exercise those guts, then it always works. Then it usually works out in physics. So yes, she's totally right. Aja just had the guts to just treat I just like it was another crazy omega. And let's not even forget, omega was intimidating at one point. It looked like a Greek letter, but it's just a freaking number. So she did that. And then to go one more step, so I don't get too carried away with my excitement. If I do it again, we're going to do it again. And we'll bring down the I and omega again because it's chain rule again, because that's why they call it chain. So it would be like this, and then, right? I hope everybody's still with me. And then we go, oh, wait a second, right? I mean, that would be like sorry. So the answer to the first derivative was this, and I guess that was 1, and then this is 2. Then this would be the answer to the second derivative, but before I circle it, like technically it's correct. And technically, I guess I would give full points on an exam if that was your answer and it just ended there. But if we want to make any headway with this or any insights or understand anything, we would notice, like, wait a second, we can simplify. I squared, well, if Exactly. That's beautiful, Catherine. Yes, exactly. I don't know why that turned into a song, but totally what Catherine's saying, which is totally dovetailed off what Aja was saying, which was totally dovetailed off what Juanita was saying. And yes, like the point, what's nice about I is that if I is square root of -1, then by definition, I squared is -1 for sure. Like it's not a leap. I mean, it is a leap. It's a great insight, but it's not out of nowhere. It's totally just the knowledge that we have. So in other words, what Catherine's saying, I'm going to go to the next page. Well, no, I'm not. So what Catherine's saying is this. And then, oh, look at, sorry, chat. 1 second. Yeah, awesome. So that's that. So if the question asked, I don't remember if the question asked. Right, so that is the answer to the second derivative, circle. So then on the next page, when it goes to K, now we see the point of why someone introduced that. That K is X equals X equals E to the I omega T a solution right? So in other words, the I does address the negative sign problem. Like the I is some weird, clever way of making the negatives work out. Like we could putting the negatives anywhere else. And I could have tried putting them other places. It didn't work. But putting the I in does work. Which actually is a mathematically interesting thing. It shows that somehow, even though exponentials are wildly different from trigonometrics, like exponentials go whoosh, or they go whoosh, whereas trigonometrics go meh, meh, meh. Apparently, oh, sorry, yeah, go, sorry.
Can you turn to the previous page?
Oh,
for
sorry.
1 second?
Yeah, of course, absolutely, yes, sorry.
Okay, I'm fine now.
Okay, great, thanks.
Thank you.
No problem. Okay, and I just got to no, thank you. Oh, wait, okay. 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 So, sorry, one last thing, sorry. Okay. All right. So so mathematically, for anybody who just likes math, it's sort of interesting. It says that somehow weirdly, if we put together complex numbers with exponential functions, we somehow get the same effect as trigonometric functions. Like that is actually what we're saying. Now that may be a mathematically abstract thing to say. Physically, what we're saying physically here is that actually oscillators can be described with complex exponentials. In short, what I'm saying is I is an actual number. I mean, that's the fast version of what I'm like. We can call it imaginary, but it's no more or less imaginary than any other numbers. And the truth of the matter is, when we want to describe oscillating systems, especially electronic oscillating systems, as it turns out, physicists use e to the I omega t all the time. They use it interchangeably with cosine omega t, because it ultimately means the same thing. I is not a fake idea. It's a very powerful actual idea in electronics, in electrostatics, and in quantum mechanics. Just for anybody who cares. Now, what does that have to do with your exam? Just this much. Just knowing that, oh, e to the I omega t is a solution. In other words, this is a harmonic oscillator. Physically, I'm saying we did just come up with another way of describing. Anything that's like a mass on a spring or a pendulum going back and forth, or any clock, any system that's going back and forth, which is what we care about right now in this course, can be described more than one way. It can be described with cosines, which is generally what we do in the class, but it can be described with complex exponentials like this. I mean, that's the takeaway here. I'll say one more thing very quickly as to why. It does open up a whole interesting world. You can care about it or not, but that's the takeaway for the exam. I mean, that piece. Is this part J? Yeah. Last thought on part J. Sorry. Actually, wait, sorry. Bear with me for a second to just copy this. Oh, yeah. What just happened? I just lost my board. Sorry, hold on. I don't know. I just lost it. Or did I? I can't write on my board. Bear with me for 1 second. Yikes, what is going on? Wait, am I? What is going on? Hold on. Okay. Okay. Okay, notice this, and this all seems random. I'm looking at the chat. And we'll get back. Oh, yeah, a question in the chat. Do we use antiderivative for anything in physics? Absolutely. And then we are doing that right now. If you think of, I mean, absolutely. Um, I mean, all of these differential equations in effect are using antiderivatives and integrals. And you'll see more of it in this course, but integrals and antiderivatives are possibly arguably bigger in physics than even derivatives. I'm just responding to something in the private chat. Do we use antiderivatives in physics? Another way to put it sort of quickly is we use the derivative anytime we're looking at one point in space and time, like instantaneous velocity, instantaneous acceleration, free body diagrams. But we use antiderivatives and integrals anytime we're looking at a finite interval or segment or region in space and time, such as when you're looking at work, like force times displacement over an interval. If you're looking at work, or you're looking at potential energy or kinetic energy, all those things are all integrals and antiderivatives. So definitely yes. But okay, getting back to this, I mean, good question. Getting back to this, did I just lose? Wait, sorry. Getting back to, oh my God, did I lose you all? Oh no, okay. Getting back to this, just notice here, I just want, just as far as, again, trying to tie the math to the physics, basically trying to say why all of a sudden in a physics class, like why all of a sudden are we talking about like e to the I, blah, blah, blah. Like what does I have to do with E, and what do they together have to do with oscillators? Oscillators are most easily pictured with sine and cosine, but look at this for a second. If you have a function of x e to the x, you know, if you take the first derivative, you get e to the x. You take the second derivative, you get e to the x. Take the third derivative, you get e to the x. Take the fourth derivative, you are, of course, still at e to the x. You're back. If, in other words, if you take 4 steps, differentiating steps, you're back to the original. You don't need to take all those 4, but if you do take 4, you're back to the original. Now, why am I taking 4? Why am I looking at that? Well, because with sine, if you take a derivative, you get cosine. Take another derivative, you get negative sine. Let me make that darker, right? You get negative sine. Take another derivative, you get negative cosine. Take a fourth, and you're back to sine, right? So what I'm saying so far is with both of those functions, as long as you take 4 steps, like a maximum of 4 steps is needed to get back to the original function, right? And again, 4 iterations of feedback, if you like. Like that's a similarity between e to the x and sine of x, is that if you churn the derivative crank 4 times, you'll get back to the original. Note it now, look at, right? That's a similarity. Again, a difference is how the negative signs work, but that's a similarity. Now look at this. Now just notice this is not a class in complex numbers or anything like that, but just notice if all we believe about I is that it's the square root of -1, if that, oh, did I just lose the board again? God, sorry, this is an internet problem. Oh, that's so frustrating. I'm going to get back the board, but while I do that, I'm going to say this. Wait, no, where did the board go? Come on. What is going on? All right, you got to move or something. Okay. Notice this with I, if I is the square root of -1, if I is the square root of -1, well, first of all, any number to the 0th power is 1, right? I to the 1, I by itself is by definition square root of -1. Someone in the class already, I think it was Catherine, it might have been Agia, maybe both. Someone in the class already pointed out, I think it was Catherine, that I squared, if I itself is a square root of -1, then by definition, I squared has to be -1, right? then I cubed, let's just do this for, you might have seen this before in math, but let's just note this for a moment. If I squared is -1, I cubed has to be I times I squared, right? I mean, that's just by the rules of exponents. And so what is that? That's -1 times I, in other words, negative I, right? I cubed must be negative I, just by the definition of I. And then I fourth has to be I squared times I squared, which is to say -1 times -1, which is to say 1, right? And so, and similarly then, I to the fifth has to be I to the fourth times I, which is to say 1 times I, which is to say I. What I'm saying is, look back, I'm just saying it's not, this is a weird coincidence, but it's not a coincidence. If you take exponential functions and you cycle them 4 steps, you'll get back to the exponential. You take sine or cosine, cycle it 4 steps, you'll get back to the sine or the cosine, whichever you choose. Take I, cycle it 4 steps, you'll get back to I. There is definitely a relationship among all these 3 quantities, and you put them together and you get a function that oscillates with infinite differentiality. Again, maybe it's a math point, but it's also just another way of trying to reinforce when you think of, oh, and this part, okay, this is like what Aja was saying before, or someone was saying before. No, this wasn't, I'll look in the chat. This was, oh, it was Aja. Yeah. So when Aja said, wasn't this on homework 1? Yeah, this is all, I mean, this is why homework 1 is homework 1, because homework 1 is kind of like the book out of which comes all of this stuff. Like, this is that business when we were in the middle of homework 1 talking about, oh, the velocity, but the acceleration, but the jerk, but the snap, but the crackle, but the pop. Like the derivatives are running over and over themselves, over and over, and cycling. In other words, an oscillator is not just a cycle. It's a cycle.
I need a chance. Yeah.
Okay. Like there's
Okay.
cycles within cycles within cycles.
Drive?
There's cycles of different, there's cycles of position, and there's cycles of derivatives, and there's cycles of derivatives, et cetera, et cetera. Okay, so Edie, yes or no? Or good? Or good? Or good? Okay. Okay. And if it's a question, definitely, I think it might be just a mute thing, but okay. All right, so back to the homework now. Oh, okay. Okay, this is now part 2 of the homework. This is just to refresh you on cosines and make sure you're cool with cosines and make sure that you're not bothered even when things are thrown into the cosine term. That was the point of this. What I'm going to do right here, honestly, I'm going to try my best right here just to write out the answers as fast as I can right now. I'm not even going to talk about them. You're not going to be explicitly, this is practice to make sure you're good with cosines. It's not explicitly on the exam, but you do need to see the difference between cosines that have a phase constant and cosines that don't. So just for closure, I'm going to quickly write down the answers here. If you've already done the homework, then you'll be able to see here whether you did it right or wrong. If you haven't done the homework, you could still do it, but you can't just write down the answers. You're going to have to show work and all that, right? So you can't like cheat by but I'm just going to write down the answers now fast so you have them. And then we're going to move on to homework 3 because we're not worried about part 3 of this. So I hope that's clear to everybody. So I'm going to part 2 of this. Okay, that's a note in case you're just blindly taking notes. I'm about to write down answers. It's for your reference. It's basically to tell you whether you later on are confused about something and should ask me a question or not. Okay, that's why I'm going to do this. But this is not the way your exam should look, and it's not the way your homework should look, the thing that I'm about to do. I'm just about to do answers. I hope that's clear. This is just for reference. Okay, so bear with me. Let me get it. Wait. Yeah. Okay, I'm going to give you, so those are the answers to the first part. I'm just going to give you a minute to, please copy them down, sort of just cross-reference them with your homework and make sure that it's what you thought when you did the homework. If you didn't do the homework, then when you do it, you can use these as a guide, but you have to show work and prove them, blah, blah, blah. It's just to make sure that we're all on the same page with cosines. That's part A. I'll do part B in a second, but just gonna give you a second to copy it down or whatever. And also if you're pretty sure that I made a mistake somewhere right now, let me know. Maybe I did. I don't think I did, but obviously if there's a mistake here, let me know, but I think they're right. They're also secretly just kind of practice with like radian. Oh, this all assumes radians. This assumes that we're taking the cosine of things measured in radians. So I think like the cosine of pi radians, for example, is -1. I think the cosine of pi over 2 radians is 0. I don't know if that, but okay, so that's that. I'm going to go to the next page in a second. You can tell me to go back if I'm going too fast. Again, if you look through the practice exam, you'll notice there are no questions that explicitly look like this. It's just that if you can't do this, a lot of things in the exam would be confusing. It's like that sort of thing. So it's, it's like drill. I don't know. So that's A. Now I'll do B. Stop me if you want me to go back. B is Just happened again. Oh my God. Sorry, that's my board again. That's my internet. That's my emotional reaction. Are we still there? Thank you. I totally appreciate it. Okay, wait. Oh, good questions in the direct chat. I'm sorry. Wait, thank you. Okay, totally appreciate the like the comforting in the direct chat about this like internet thing, but then also a question in the direct chat. Yeah, is graphing a valid way to get the answer? Yes, it is. Wait, that's a really good question, especially say this for an exam. Actually, I'm going to read the exact question. I'm not going to say the person's name, although he or she should totally submit this for blah, blah, blah. But she or he said, is graphing a valid way to get the answer, or do you prefer the math? So first of all, it's totally a valid way to get the answer. If this were an exam, as long as you like make the graph clear and you point out what you're doing with the graph, that could be even better than something else. I totally consider, I just want to pause for a second. I like the way she or he put that, or do I prefer the math? Like I consider graphing's math. Like I know what, of course, the person means, like, do I prefer computations or something? The truth of the matter is, to all of you, one of the reasons I like this question is when it comes to your exam, actually, the more physical you can be, the more diagrammatic or graphical or Englishy, the more you're not just giving me raw computations, the better we both are. Two reasons. One, the deeper you go in math, the more you find math is not just about computation anyway. Computation is like the scratch work or the stuff that sort of justifies our thoughts, but the computation is not our thoughts. Or it's certainly not the sum total of them. Second of all, this is physics, not math. So the more you can make the math physical, the better for both of us, the better you really are doing physics and the more you're showing me that you really understand. So this is why I'm always asking for diagrams, even when I forget to ask for them. So yeah, totally, you can show this on a graph. If I ask questions like this or anywhere on the exam, please also understand every solution I ever try to do on this whiteboard that keeps fading, I'm trying to give you a model of what I would give full credit for. I'm trying, and sometimes succeeding more than others. Like I'm, trying to walk you through and give explanations with English, with pictures, but it is just a model. It's what you see on the whiteboard is my personality, right? Like it's me doing this. I think you can tell from the way I'm doing it that I at least know what I'm talking about, like for this material. Like hopefully you see I'm just comfortable enough with the material that I can try to say it more than one way, but it's always in my handwriting. It's always with my perspective. It's just my personality communicating the physics. That's your goal on the exam. You don't want your exam to look like mine. Mine's just an example. Just like if you wrote an English essay or a history essay, like even if we're both writing about the COVID virus of 2000, whatever, even if we're both writing about the same event, ultimately you'd want your essay to be very different from mine, even if we're also writing both in the language of English. Like the more comfortable you are in English and the more comfortable you are with the events you're talking about, the more your spin would shine through. That's what you want. You want to get comfortable enough with this physics that you give me your take on it. So it might be all graphs. It might be very different from the way my notes look. Anyway, okay. Okay. Back to, okay. So that's that. Okay. So I think that's B. And now I lost a sheet again. I'm losing everything. I'm losing my mind. Where'd it go? Where's this? I don't even know if I've lost you all. Are you still okay? So 8, find a value. Oh, find a value to you. Oh, did I just do the last one? oh. Oh yeah, that was right. I'm sorry. Okay. Right, right. Right. Okay. So those are the answers. Again, I mean, we could talk about them all day. I don't think it's worth it. You can definitely put any questions about those in the chat or text me, call me about any questions about those, et cetera, et cetera. But I think if you got the right answers to those, or when you're practicing and you do by yourself, then I think we're on the same page about how cosines and sines work. I'm all about the unit circle, by the way. Like, I mean, that's how or put one lat. If you sort of get sines and cosines, but you always confuse them, perhaps, I mean, that's a place where a lot of people are. If you sort of think you sort of understand sines and cosines, but you confuse them all the time, or you're not totally comfortable, the two big things I would say about sines and cosines is one, SOHCAHTOA. It is all about SOHCAHTOA a lot of the time. Like, you know, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent. That's super important all throughout physics. But the other thing is, if you're going to remember nothing else about sines and cosines, if you sort of get them, but you sort of confuse them all the time, just remember the main thing to remember is that sine of 0 equals 0. Or sine is sometimes I say to people, sine super, cosine crappy, or sine super, cosine counterintuitive, meaning they both work the same way and all that, but sine is the one that starts at 0, as you kind of hope, like the whole graph, like starts at the origin, nicely right in the middle of the whole graph paper. Sine of 0 equals 0. And as the angle gets bigger, the sine gets bigger. Like if you were inventing a function, you would invent it like that. As you make the X value bigger, the Y value gets bigger. Sine grows as the angle grows. It's cosine that's crappy and backwards. Cosine of 0 is 1. And as you make the angle bigger, the cosine gets smaller. That's not an explanation of anything. That's just like a memory thing. If you sort of get sine and cosine, but you confuse them all the time, just remember sine super, cosine crappy, or sine of 0 is 0. Like it's all S's. It's like a snake. Sine of 0 is 0. That's what I always remember. And I sort of bring everything back to that, if that helps. It may not. But all right, that's the deal with sines and cosines. Again, please remember, I'm going to write it now clearly. Why is this? I'm going to write clear. Okay, just if you're going through this while you're studying or whatever, I'm saying clearly to everybody, part 3 of homework 2, you are responsible for, like you did get points if you handed in, you don't get the points if you don't, blah, blah. We'll get to it eventually, but it has nothing to do with midterm 2. I'm just like, I'm postponing it. So we're not dealing with it now. I'm skipping it now. And please understand that's because you don't have to do anything with it on midterm 2. So don't worry about it. Therefore, I'm now going to homework 3. Okay, sorry. Oh, what? Oh, what happened? Wait. Oh, wait. Oh, yeah. Sorry. Yes. Direct message person. Totally to anybody and everybody. You can and should still hand in all of this. Homework 2, you can still totally hand in even the first 2 parts, even though I just did all this. Now, again, at this point, and certainly part 3, you can and should. And okay, I'll answer that. Well, okay. So to Shankia's question, again, you're having this midterm and you're having the final. That's it. Those are your 2 exams. And then all your lab stuff together counts together as one big exam in effect. Right. Okay, cool. Thank you. Thank you for bringing a circle. Okay. And as far as this exam, what's on it is no more than whatever's in the practice exam that I just posted. So part 3 of this homework is not part of it. You totally can still hand in part 3 for points. You can hand in part 1 and 2 for points. I will say to everybody now, like now at this point, and you notice, hopefully you notice we are going faster and faster. Like if maybe it's still too slow for some people, I don't know. But we're part 3. Yeah, that's a fair question, Juanita. Yes. In order to do the final exam, you'll have to deal with part 3 of this homework, but by the time we get there, I will come back and talk about it. Like I will, you're not gonna have to do it without me teaching it or something. So yeah, you will ultimately have to understand it and I will talk about it. And when we get there, I'll say, oh, we're going back to the old homework 2 now. Like, so that's why we sort of put it in the box, but, and you could still hand in the homework then for the points, all of you. Okay. But now let me just say clearly though, from here on, now we've done all of homework 1. We've done as much as I want to of homework 2 right now. You guys can still hand in any of those parts, even though we went over them. But now it's kind of your job. If you hand them in, don't just copy what I wrote in the notes. Use the notes to make sure you understand it and then show me that you understand it in the homework. Just know that I can tell the difference and use that, just like on the exam. Like I don't consider it cheating to write down things that you've learned from somewhere else, whether it's me or Google or Khan Academy. Like that is not cheating. That is called research and learning. But the thing about physics, it's just hard enough that even when you see someone else do it, it doesn't mean you get it. And you all know the difference, right? I can tell for almost all of you at this point, there are things we've said in this course that people totally get and always did get. There are things we've said in this course that people didn't get before, but get now. And there are things that we're talking about in this course that people still don't get. And we all know the difference in the feeling. What I'm trying to urge all of you is just because you don't get something, don't give up on getting it. All of you are so smart and so successful. You couldn't be in this course unless you had already passed a lot of really hard science and math courses. We all know that. The problem with that is that a lot of you are getting used to in life doing things fast. You're used to being the smart person in the room or the knowledgeable or the hardworking or all 3 person in the room. So you're used to classes where as long as you do your work and you pay attention to stuff, things immediately make sense. And then you just have to like memorize them or whatever. I mean, I'm not criticizing anybody, but a lot of us have gotten used to the idea that school is a ton of work composed of little things where as soon as they're presented to us, as long as we're paying attention, they make sense. And now we have to like store them all in our brain. Physics isn't that way. Physics doesn't make sense when you first look at it. And then you look at it deeply enough and it does make sense. That's what we're practicing here, is the skill of going from not understanding to understanding, right? It takes a different type of work. Why am I yelling right now? I'm yelling right now to urge you all to realize that there's a big difference between writing down some stuff that someone else wrote versus writing down your understood version of it, right? And the difference is clear to anybody who understands, right? So this is why physics is unusual, at least in this college, where you can open everything to do our exams, including mine, and you can hand in homework that I've already gone over in the class. I don't care. In fact, I want you to, because by the time you hand in something, I want to look at it and know whether you understand what you wrote or not. Your job is to only write things that you understand and show me that you understand them by the way you wrote them. It's like essays in a foreign language in that regard. And you know the difference and I know the difference. And that's what you're going to be tested on the exam. So that's a long way of saying you totally still can hand in homework 1. You totally still can hand in homework 2. Just hand it in because you now understand it. Don't hand it in because you can now copy it, because I know the difference and you know the difference. Okay. Going to homework 3 now. Going to homework 3. Going to homework 3. I'm going to homework 3. Homework 3 looks like nonsense when you first look at it. I'm sure to a lot of us, it looks like total nonsense. But if we now relate the things that we've been doing, particularly if we think about what we actually said yesterday, we'll totally see how homework 3 works. Just to pull it up. I'm sorry. Where'd it go? Homework 3. Oh, and please also understand. So I'm about to pull up homework 3. And you also might say, oh my God, he's only up to homework 3 now. Also notice that this entire homework 3 is one of the 5 problems on the practice midterm. Like if you understand homework 3, it's literally is one of the problems on the midterm. I mean, it may or may not be on the real thing, but it's definitely on the practice. So, and at worst I'll change the numbers, but it is what it is. So I'm looking at it. Okay. So homework 3 says, imagine or consider. Okay. So we're being given, we're all of a sudden it's talking about temperature, it's talking about weather. And again, like if I'm maybe you or if I'm me, I'm like, weather, temperature, when the heck did that come into this class? Like what the, like what, he's never told us anything about weather. He's never taught us anything about weather. Right. I haven't taught you anything about temperature, but I'm saying now, imagine there's a temperature system that can be described by this differential equation, where D stands for temperature. And apparently we have data or graphs or lab experimental information to show us, to put together that apparent, oh, and I see there's stuff in the chat. I'll look in the chat in 1 second, sorry. But just imagine that we have a temperature system where D stands for temperature. So temperature could be anything. It's any measurable dependent variable. It happens to be temperature in this case, where D obeys that differential equation, where the second time derivative of D equals a negative times some constant times D itself. And imagine that we know the initial condition, that we know that the very starting temperature, the temperature when T equals 0, the temperature when we look at it happens to be 300. Imagine those givens. What can we infer about it? And now we're going to go. So it's a physical question. It looks like a new physical chapter, temperature, but it's not, because what this is, the minute we look at that differential equation, what we're going to say in our mind is, oh my God, that's the differential equation for simple harmonic oscillation. This temperature must be harmonically oscillating. It happened to be a D here. In some of the practice exercises we were doing the homework, it was an X, or in the lab, it was a theta, or in some of the other practice exercises, it was a Z. We're trying to get used to the fact that it doesn't matter. If the dependent variable can be described with derivatives this way, then the dependent variable is oscillating harmonically. That's the thing that we're trying to get at. That's what this homework is going to be about, all these questions. I'm going to do them right now, but I think there's stuff in the chat. Pardon me for a second. Sorry. Hold on. I think we did. Oh, okay. I did answer them. Yeah. Good questions from Shankia and from Juanita. I think I answered them. Yeah. Well, yeah. Shankia, thank you for it. And part 3. Yes. Part 3 will be in the final, but definitely don't stress about the final right now. But yeah. Okay. So here's the givens. And notice, by the way, it's a little bit subtle. Notice we're getting used to with differential equations. You kind of always have to be given the equation itself and an initial condition. Right? Like with homework 1, we had a mass on a spring going back and forth, and we were told that at the very first spot, when we first started looking at it, it was at a spot of 15 centimeters to the right of equilibrium. Like we're always given an initial condition along with the differential equation, and then we're asked to solve. So these are the givens. Sorry, this is a given. I'm going to go on the next page now. Question 1. So I'm going to write the givens again. Sorry. Okay. So we're given this. And again, D is just some variable. It could be anything. It could have been Z. It could have been X. Could have been Y. It's a little unusual that it's a letter from the beginning of the alphabet, but it doesn't matter. And 121 is a number, but it's a constant number, and it's preceded by a negative sign. And it's preceded by, it's preceded by a negative sign. So we have a Hooke's law situation here. So question 1, I believe, is how much time does it take? How much in seconds, how much time will elapse before the very next time the temperature returns to 300? Okay, right. So the temperature is starting at 300 degrees Kelvin. We're being asked how much time will elapse before the very next time the temperature is again 300. That sounds like an obscure question. That sounds like, what? We've never dealt with anything like that before, but we totally have, right? What it's asked, and I know you know this, I'm just going to put in my words. What we're being asked here is, what's the period, right? I mean, and this is totally like a labby thing as well, but we're being asked, what's the period of this situation? If I didn't know anything, I mean, I don't know how to get T out of the, I mean, if I'm just walking into the class right now, this is very obscure. Like, how am I supposed to get T out of that crazy looking equation? But what I'm supposed to recognize is I'm supposed to recognize, well, all right. So what we're being asked is, right? We are being asked the amount of time it will take for one cycle of temperature values to occur. The temperature values here presumably are going to go from 300 down, all the way to 0, all the way down to negative 300. Whoa, is that even possible? No, actually, that's crazy, but okay, whatever. And then back, up to 0, back to 300 again. And they're going to do that forever. How do I know? Because that equation is the differential equation for simple harmonic oscillation. Like, that's my job as a physicist now, to recognize that equation whenever it pops up in whatever disguised context. This is, I suppose, so if I were doing the homework right now, I should say that. I don't know why I wrote it up there. I should say, like, I know this is a harmonic oscillator specifically because that equation has that form. Second time derivative of variable equals negative times constant times variable itself. And that means it's a harmonic oscillator. Therefore, first of all, therefore, it definitely is cycling. It definitely is oscillating. It definitely will have and because it's oscillating harmonically, well, I'll write this on the next page. In English, when the mere fact that this thing was described, like, I'm not saying we're supposed to know something about weather independent. I'm not saying, didn't you read the textbook? Don't you know that temperature is always a harmonic oscillator? No. First of all, there's no textbook to say that. Second of all, I'm not saying that's true. I'm not saying temperature is always a harmonic oscillator. And I'm certainly not saying that if it were, you were supposed to know that for the class or memorize it. What I am saying is that whenever I see anything of that math form, if anybody tells me that something is following the form of this math equation, that means simple harmonic oscillator. Whatever variable can be described that way is harmonically oscillating, definitely. And the reason we're spending all this time on that is the minute we know that, the minute we know something's a harmonic oscillator, we know a lot about it. We know a lot of special properties of it that are calculable, measurable, and predictable. Specifically, if something is a harmonic oscillator, then we know it's oscillating, it's wiggling, it's repeating, it's cycling back and forth at a rate which is constant. That's already interesting. A constant rate, and a rate that is so constant that its constancy is independent of how you set up the system. This goes back to like a week ago when I got off on what may have looked like a big sidebar talking about Galileo and the chandelier and all that. The importance of that whole sidebar discussion was oscillators go back and forth at a rate that has nothing to do with how you set them up, a time rate that has nothing to do with how you stretch them in space. They will keep time regardless of how much space they're set up to take. And the rate at which they go back and forth in time is mathematically what we call the angular frequency, but physically what we call the standard frequency, and inversely what we understand to be the period. The angular frequency, the standard frequency, the period, they're all linked together as per yesterday's lecture, and they're all a constant that falls immediately out of the differential equation, totally independent of conditions. That's in English what we know immediately the moment I say, oh, d2d dt squared equals negative 121d. All of this is known to me. That's why this is such an important type of equation. Now, mathematically, what I'm saying is sorry. Oh, I'll say it back. Say it the other way around. Yes, yes, totally, totally, Juanita. Yes, totally, totally. I'm dragging this out because I'm trying to explain it to everybody and because I'm the teacher and blah, blah, blah. But yes, that's where I'm going with this, Juanita. Awesome. Yes, and totally put that in for a million zillion points in the for right or wrong portal, which I should probably make another one because some people are already using it and should use it more than once. Yes, totally, Juanita. Yay. Can I say yay? By the way, yay backwards is yay. Okay. Okay. Sweet. Oh, and that, oh, I like that. That totally, Edie should get tons of points for that too. Everybody. Like, notice she just said agree. Like, she wasn't the first. Like, that's helpful. That's not cheating. That's called scientific collaboration and human averration and class participation and lots of other things that rhyme. Yeah, so that's awesome. Thank you, Juanita. Thank you, Edie. And I'm not being sarcastic. You'll know when I'm being sarcastic. But I did lose my mind. Oh yeah. Okay. So what I'm saying now, and this stuff that every time I write it, it sort of looks like gibberish, maybe because it's meant to be really in general. But the more you get used to it, the more you'll see. I'm saying in general, if we have d of something, or put another way, I'm saying, wait, what? Put another way. So this is just expanding out what those two just said. So if you already get it, you already get it. But right, there's just different ways of writing the same thing. I'm saying whenever we have that differential equation is recognizable because the second time derivative equals negative times some constant times the variable. I'm saying now then we automatically have an oscillator, a harmonic oscillator, and the angular frequency of the oscillator is always the square root of whatever that constant is. That is why we often call that constant omega squared. We're just trying to say that the omega, the angular frequency, is the square root of whatever that constant is. So wait, I'm just looking in the chat. So in this case, Oh, cool. Oh, yeah, we got the agree. Okay, right. So in this case, right, hopefully you can see that. And that's another thing for those of you who do think you know what's going on. Like when I say it one way, then your next goal is, can you see how the different ways I say something all actually match up? Like you get it. Anyway, so I'm saying here, and I can go back. Right, we have that. Therefore, right away, I can say, and also we know we're told this, right? Those are the two things we're told. Therefore, right away, I know that D equals D naught cosine omega t. And we could add a phi, but it's 0. I'm not worried about that. Well, plus, since we just started learning about this yesterday. Remember, we just learned yesterday that there could always be a phi in there, and phi refers to the delay or the head start, but there is no delay or head start here. So we're still back to sort of the easy thing, the easier thing that we started the year with. In other words, okay, that's just like a sidebar detail, but I'm saying we know that D equals D naught cosine omega t. We're told that D naught is 300. And what I'm saying here is necessarily here, it's that omega equals the square root of 121, right? Like I'm saying, we know right away, just by looking at the form of this equation, omega squared equals 121. Omega equals the square root of 121, which is 11, plus or minus 11, right? So I'm saying, I'm going a little fast. I'm looking at the time, going a little fast, but it looks like at least 2 people in the room totally understand what I'm saying. And obviously a lot of you have handed in this homework. So a lot of you know what I'm saying. I'm saying here, just to recopy here. I'm just recopying in case we. So omega equals 11. Literally, in other words, let me be more, well, we'll get to this. Omega equals 11 radians per second. That's the angular frequency. Like if we were to make this a cosine graph, if we were to plot out temperature on a graph, temperature on the y-axis and time on the x-axis, we would see a cosine graph. And the number of wiggles, the number of humps that cosine graph would have per every period of 2 pi would be 11, right? That's what we're saying, 11 radians per second. But what the heck do radians have to do with temperature or anything? This is the part where Juanita's thing comes into play. Omega is angular frequency. By definition, standard frequency, and I'm just dragging this out. Like I do agree with Juanita's conclusion. If you wrote Juanita's conclusion in your homework, you're good. Like, and if you understand, you're good. I'm just trying to explain it again in case. I'm saying that's number of radians per second, but there's 2 pi radians in every cycle. That's the memorizer to always come back to. Every cycle has 2 pi radians, or every circle has 2 pi radians. Therefore, F by definition is always omega divided by 2 pi. Right? So in this case, it equals 11. In other words, 11 radians per second divided by 2 pi radians per cycle. And the radians cancel. So we get, so we get 11 over 2 pi cycles per second. And that's approximately 11 divided by 6.28, approximately. You could even say 6, it wouldn't bother me. 6 point, which is approximately, no, I don't even remember. I think that's, oh yeah. And then there's one more step to do to get Juanita's equation and to get the answer. Sorry, I totally, hold on. 1 second. Right, okay. So approximately 1.75, I should have known that, cycles per second. Not that anybody's asking that yet. I'm getting all the steps. In other words, just so you know, I'm saying that F, not that anybody asked it, but that's how I'm getting there, equals approximately 1.75 hertz. That's the standard frequency. It's doing about 1 3/4 cycles per every second. But what the question was asking is how many cycles, how many seconds are there per cycle? So T, by definition, equals the reciprocal of that, which, and now here's
Can
the
you
one.
go back 1
Oh,
second?
sorry. Yeah, absolutely. Sorry.
You can move on. Thank you, Professor.
Thank you. All right, awesome. All right, so, and again, I'm just putting in an extra step. Like well, anyway, yeah. So that's the standard frequency. Now, period is the reciprocal of that. That's just like, or in other words, frequency is cycles per second. Period is seconds per cycle. So I'm just flipping them. It's like saying if I run 4 laps around the track per hour, then that means every lap takes me 1/4 of an hour, right? That's just the logic of what I'm saying here. But put another way, equals. This is the equation that Juanita put in the chat, and it's totally right and it's totally valid. Well, yeah. You could do it whatever way. And what we get is like 0.5, it's like 0.578 or something. Hold on. I just lost my, sorry, I just lost. It is like, I know everybody got, most people did get this right on normal. Where did it go? Where did it? Hello. I just lost. My, well, oh yeah, yeah. Again, I added a couple extra steps that some of you might not. Some of you might have just done T equals 2 pi over omega. I totally get it. That's fine. I'm just explaining why that's true. But in the end, what we're saying is the period of this oscillator is about 0.571 seconds. That's how much time each cycle takes. So that's how much time will elapse until the very first time it returns to a temperature of 300. That's the answer to the first one. And oddly, one thing that's a little bit odd about this homework sheet or this test problem, one thing that's a little bit annoying is right at the top, I sort of asked the hardest, most involved question. Like if you can do all those steps, then the kind of the rest of the homework, I mean, I probably should have broken that down into steps and asked it later on or something. But if you can get that, then and if anybody's looking in the practice exam, this is problem 4 of the practice exam. I put point values and everything, but it's just literally this problem. So we do that. And from here on in, it's, the big insight is just recognizing that it's a harmonic oscillator. Once you recognize that, that's number 1. So net 2 at 2 says in kelvins, find the temperature at the moment precisely 200. Right. So 2 asks at T equals 200, what is the temperature? Like we're using capital D to stand for temperature for, I don't know what reason, but so question 2 is just asking what's the temperature at 200 seconds. This, going back to Ajia now, this question 2 is identical to question 9 from homework 1. You'll recall that we spent like 2 weeks doing homework 1 practically. It took us so long to get to question 9. And then we did all this work to answer it because question 9 was the first time we'd ever seen this before. We had to figure out the differential equation from Hooke's law and then solve it. We did all this work to get question 9 of homework 1. But then we finally got an answer. And now we got that answer, we can use it all the time. Like we did all that work back then so that we could finally understand if D2T this equals this. If we're given that, then what we now know, what we've spent all this time doing, and the now powerful tool we have is then D equals 300 cosine 11t. right? Like that's the point of understanding harmonic oscillation, that if we know that differential equation, we know this is the solution, right? And that's what we've been using in part one. So now it's a plug-in. In other words, we did all of that work to give ourselves something we can plug in for the rest of our lives. So I'm going to plug in finally now. So I'm going to the next page. Stop me if, or you could turn me back, but I'm saying this is question 2 continued.
Can you go back one
Yeah,
second?
sorry. Yeah,
Okay?
I knew it. I knew I was, yes, sorry. Okay.
Thank you, Professor.
No problem. No problem. All right. Right. So pleasure. So, okay. So yeah. So this is homework 3, question 3. Oh, nice. Okay. So that's okay. Okay. So okay. So that's, I mean, that is literally a plugin, but it's a plugin that's only, and of course we all are always looking for plugins. Who doesn't want a plugin? But it's only a plugin if you understand all the things that come before it. All right, let me look in the chat. Oh, okay. Okay. So that's the answer to that. I want to point out now too, actually, when I say that, so again, this is a problem that is on the practice exam, very high chance that it's on the actual exam, and you're just going to show that you understand it in your way. You know, I'm giving you the answers now, but I am warning you, of course I could change the numbers, and I'm telling you right now, if this is on your actual exam, I am going to change the numbers, because even though I've been giving out this problem for years, it just occurred to me for the very first time ever that this is impossible, these numbers. I never thought of this before, but it actually is impossible, because if this is an oscillator, it would oscillate back and forth between 300 and negative 300 degrees, right, Kelvin? But Oh yeah, that's really impossible. Yeah. Well, I guess there's no rule that says zero has to be. I have to think about that. These are wacky numbers because things don't get to negative. I mean, 0 Kelvin is absolute zero. 0 Kelvin is like all motion stopped. So nothing in the universe is getting to negative 300 Kelvin. But whatever. This is the correct math, and this is the correct way to do it. That's the answer to that one. We have 9 minutes. We're just going to keep. I'll definitely take questions if there are any, but other than that, I'm going to keep trucking through this problem. Again, I think the hardest part really was part one. If you really understand part one, then that means you understand it's an oscillator, and all the rest is just a way of making sure we understand oscillators. So 3, it says, in what units must the 121 be measured? The 121, okay, and this is kind of important. I mean, it's not hard, but it's important. The 121 is the constant in that differential equation. Granted, this differential equation happens to be talking about temperature, i.e. the dependent variable is measured in temperature units, but that doesn't matter. It always works for all of these oscillators. 121 is the square, is the constant. It is the square of the angular frequency, and the units of angular frequency are always in radians per second, right? Always. So the 121 is definitely in radians per second squared. Like the answer to this question is omega squared, the 121 is in radians per second squared. You can, and that's the answer. And do note, like all the questions asked, and it's just trying to get that across, that constant, no matter what your situation is, that constant is always the square of the angular frequency. It is always radians per second squared. If you just wrote 1/second squared, that'd be fine too, because radians technically actually are not actually a unit. Remember we said radians are actually dimensionless or unitless because a radian is actually a pure ratio of meters per meters, and the meters cancel out. So that's fine too. But just one thing, if this were an exam, or if this is the exam, and I ask in what units are the 121 measured, you show any work you want about that 121, just like I did. You do whatever you want with 121, but your final answer has to be units. Don't tell me that your final answer is 121 radians squared per second squared, because then I don't know if you know what the question is. Like, right? The question is not what's the constant. The question is, what are the units of that constant? So the answer is radians squared per second squared. Okay, so that's number 3. Then 4, and we're, okay, what time is it? Okay, we're going to do this. So then 4 is meteorologist. Okay. 4 says meteorologists conjecture that this weather system can be modeled as a huge concentration of hot air being pulled and pushed by pressure differentials that behave as though they were elastic bands. And by the way, again, even though these numbers are crazy, that's all reasonable. I'm not saying that all weather systems act like this. I'm not saying that every temperature perfectly obeys this, but I am saying it is a model that comes up in a lot of natural systems. In some natural systems like quantum mechanical, like atomic systems, or astronomical systems, this math is super precise. In other systems like weather or viruses or bacteria, it's less precise, it's more approximate, but it totally is a model that is used all the time, this oscillating model. So it is reasonable to imagine a weather system being pulled and pushed as though by elastic bands. So then it assumes, so we say, assume that this mass of hot air has a mass of 8 times 10 to the second kilograms. In other words, 800 kilograms. If that's the case, then what is the effective K? Or you could say the effective. In other words, there is no actual metallic coil, but if this thing is acting springy, then how stiff is that springy phenomenon? It's a totally reasonable question or common question. And it is the question we're asking. Well, all you got to know here is recall. This also goes back to homework 1. If the kind of oscillator we have is a mass spring Hooke's law system, then the constant of proportionality is square root of k over m. Like that's what omega equals. And here we have omega, we're solving for k. So in other words, omega squared equals k over m. We're solving for k. So k equals m times omega squared. So it's just 8 times 10 to the second times 121. I'll just finish this right here. And I know we have 2 more minutes. Hold on, let me just do this really quick. Oh, I keep losing my calculator. I should be able to do that in my head. Sorry. So 8. And it's a K, effective K, so it's measured in newtons per meter, like force per unit length. That's the answer to that one. Now, very quickly, the answer to the next 3, since I know we have 3 minutes. The answer to the next 3, well, I guess strictly speaking, the answer is true, true, true. Well, all right, we'll do this as quick. We have 2 minutes, and I can go back if you want, but I'll say the answers first, just in case. Answer to 5 is definitely true. Answer to 7 is definitely true. And that's because of homework too. We've shown this over and over again. Like we have shown that D equals 300 cosine. Like if you take 2 derivatives of either of those expressions, you get back the original expression times a negative times the constant. The only thing that's a little bit questionable is 6. 6, most of you put true, and I gave full credit for true. But strict in the exam, you'll see. Okay, we have 2 minutes. I'm going to say this. Strictly speaking, if I just said, do these equations fit the differential equation? Then you're right. If you say true, each one of these equations, if you differentiate it twice, you get the harmonic oscillation equation. If instead what I wrote, and if you're still paying attention now, and I know we're about to go, but if you look in the practice exam, I changed the word of this slightly to make it less ambiguous. In the practice exam, I wrote, is it a solution to the differential equation and condition as presented on the top of the sheet? In other words, if I'm asking you, does this fit both the differential equation and that fact that the initial temperature is 300? If those are the 2 conditions that we have to meet here, if both of those are true, then 6 is false, just to be clear, okay? 699 is not the same as 300, right? So if you accept the 300 as part of the givens, then 5 is true and 7 is true, but 6 is false because 99 does not equal 300. As far as the homework, I gave everybody full credit or whatever, and I understood if everybody put true, 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 because I think the homework was worded ambiguously. But on the exam, if I ask something like that, I'm saying accept the differential equation and the initial condition, like assuming those 2, do these match or not? And the answers would be 5 true, 6 false, 7 true, if you take the 300 seriously. Okay, it's totally 3:55. I hope that's clear. Again, like goodbye, goodbye, goodbye. I'll hang out for a couple of minutes for whatever anybody has, but like you're good, I'm good. I'll post this, blah, blah, blah. And we'll talk all about homework 4 tomorrow. And that's the exam. Thank you. Thank you very much. Awesome. Awesome. Look at the exam tonight and come with questions. But yeah, okay, cool, cool, cool. Thank you. Bye. Bye.
Bye, Professor. See you tomorrow.
Yes, see you tomorrow. Awesome.
Professor.
Yes. Hi.
You're posting a practice exam.
I did. You've got it. I gave it to you. It's there.
I posted it today.
Yeah.
Oh, okay. Okay. I just want to. So when are you gonna post the actual midterm exam?
So, and so the answer is Thursday night, no later than 7 PM Thursday. But all these instructions, like answers like that are given in the practice exam. But yeah, I'll post it Thursday by 7 PM and then it's due 1:15 PM on Monday.
All right. Okay.
Cool.
Okay, thank you.
No problem. Thanks. So, okay. Now, I think I said, Renice, we were going to meet for a couple minutes right now, right? I think we said. So Caleb, if you want to ask a question right now, and then I'm going to talk to Renice for a minute, if that's cool. Or if you guys are still here, I don't, or wait, okay, let me start with this. Noelia, are you still here? No. Noelia, you do this every time. All right, whatever. Caleb, are you here? No. Okay. Renice, are you here? No. Okay. So I'm going, but I think it was Renice that I said I'm going to hang out for a couple more minutes just in case. Well, am I? Okay, I'm going to hang out till, because I think I told one of you that, I'm going to turn off the recording. That much I'll do. Well, bye, everybody. It's been a pleasure. And if I just made fun of anybody in the last 2 minutes, I totally take it back.